Okay, in this video, what we're going to do is talk about a couple optimization techniques that you can apply to your graphic applications to help speed things up. Now, please keep this in mind. This is just a general discussion of a couple techniques. There's several techniques out there available.
A myriad of techniques.
Yes, these are two pretty popular ones. And I'm sure you're going to quickly find, even if you're new to the world of graphics programming, that at least one of these techniques you've heard of in the past.
Right.
But we're only discussing these for the simple fact that we could easily dedicate a very lengthy VTM to each of these topics, getting into a significant amount of code, a lot of theory, a lot of lecture.
Yeah.
And that's not the goal of the in-depth OpenGL VTMs. Right. But we did want to put this lesson in to at least put you on the right path for optimization techniques.
Yeah, usually it's the whole idea of optimization, where do I start, kind of attitude that stumps people. And once you have a general idea of how it works, the theory behind certain optimization techniques, you can easily jump in and start programming your own optimization.
That's right. So I'm hoping that we provide you guys with enough information to get you started into this, yet one more branch in the world of programming graphical applications.
Exactly.
Okay, so let's go ahead and move to our next slide. So why optimize? Yeah, that's the big question. Well, in the old days, we had to optimize because, well, our computers were slow, our video cards were even slower, and we needed to come up with a way of drawing things faster, even if we did only have 500 polygons in the scene. Nowadays, we could be easily dealing with thousands of objects and millions upon millions of polygons.
So the same problem exists.
So now it's the same problem. It's just on a bigger scale.
That's right.
So why optimize? Well, let's take a look at a first-person shooter.
Right.
Here I am. I'm a character. I am looking in a particular direction. I'm looking to the south. And I see walkways and pipes and steam from particles, all these interesting things going on, right? Now, behind me is something very similar. We've got tubes and walkways and lava pits and all this stuff. Does that really need to be drawn to my viewport if I'm not looking that way at all? I can't see any of it. The answer is no. Very good, Joel. 10 points for you. Because think about it. If we're going to draw all that stuff to memory, I guess, because it's not going to end up in your viewport, right? It's just wasting processor time. Right. It's working with a lot of data that we don't need to be working with. Now, sure, there may be specific applications out there that you design that's not a game that may need to draw those out in memory for some reason. That is possible.
But even in an application like that, there would be some other optimization that you'd have to do.
You're always going to be looking for optimization techniques. Up to this point, we haven't really designed anything in this VTM that's
extremely complex.
That's been very complex. Now, I mean, if you happen to bring in a 50 million polygon OBJ file,
you might want to start optimizing.
Yeah, exactly. But in our particular case, we haven't had a need for that. But we felt it was very important that we put this into the VTM so that, as I said a second ago, you guys are at least thinking in the right direction about how to take your graphical application and apply some sort of technique that will optimize it.
Right, so that you can maintain real time if you needed to.
That's right. Now, in our case, we're going to talk about two techniques. Now, remember a second ago I said if you were completely new to the world of graphical application programming, you've probably heard of one of these, and that is the BSP Trees. That's been around for a while now.
Very long time.
Yeah.
Doom!
And exactly. Well, that's when it seems that most people who wanted to be graphic game programmers heard the word BSP Trees for the first time.
Right.
And we also have Quadtrees and Octrees, which are very closely related. Almost the same thing, just one deals with a lot more information if you want to look at it that way. So let's go ahead and start out with a discussion about how BSP trees work.
Sure. So BSP trees, what are they, first off?
Exactly.
Binary space partitions. So basically, it's a data structure that allows us to divide a 3D scene into a tree, basically.
It's a hierarchical relationship of information, and it's and basically you can only branch two ways. Right. So you have a parent, and how many children can that parent have? Two, at most. Okay, you can never have more than two branches. And we're going to end up looking at this as a positive side and a negative side.
Of a particular polygon.
Of a particular polygon.
Everything in a binary space partition is relative to some sort of polygon in the scene.
That's right.
So you start out with a root polygon.
We're always going to start out with a root.
And then every other piece of geometry that you put into that tree depends on that root piece of geometry.
That's right. And as a matter of fact, instead of saying positive and negative, I can make it even simpler. Let's just say the front and back.
Yeah.
So we'll branch one way if we're dealing with another polygon that is in front of our root polygon.
Exactly.
And we'll branch in the other direction if we're dealing with a polygon that is in the back of our root polygon. Now, why is this important?
Well, let's take this up to a higher level.
Okay.
I mean, an easier level for people to visualize. In the real world, when we're looking at something, we're looking at, if someone talks in the background, I know that person is behind me.
Right.
I know the chair that I'm looking at right now is in front of me. I just know that because I can see and I can recognize objects.
That's right.
You can't give the computer a whole scene and say,
I see where you're going with this.
What's in front of me, what's behind me, what's around me.
It's just got data.
It's just got data.
It's got
positional data. So if I wanted to say I drew a cup and some other object, I would have to check the position of that cup and the position of any other objects and see where they were in space. So I'd have to look through every single object.
You've got to deal with every single object.
Right.
But dealing with BSP trees, we're able to simplify this because if you know that somebody's behind you and somebody's in front of you and you start to break that down into some sort of hierarchical tree, then if we said, okay, we're going to start with the root. The root in this case, Joel, will be you. And you're going to say, I only want to deal with the people in front of me. Right there, you just cut out one half of the tree.
Right.
So if you had 4 or 5 people behind you, you just cut that out altogether. So you're no longer looping through all of them. Now you're only dealing with the things that are in front of you.
Exactly.
And even then we can even optimize it even further using BSP trees in how we're going to implement the data that we've now got stored in this hierarchical tree.
So basically, BSP trees are just a way for us to divide our world so that through code, which is a data structure, we can easily loop through and say where everything is without spending a lot of time.
In the end, what is a program? I mean, it's really just data, right? It's the manipulation of data.
Right.
So that's
linear execution of code.
Ooh, look at that. So why would we use BSP trees? What kind of things can we do with it? Well, hidden surface removal is the first thing that comes to most people's minds when they hear of BSP trees.
Something used a lot in the past, especially.
Exactly.
It's really useful, basically, because if you have walls in front of each other, you don't know which one to draw first.
Yeah.
If you have hallways intersecting hallways, etc., you need to know which one to draw first so that, something that you shouldn't be seeing, you're actually seeing in front.
And even then, some of you guys may be familiar with gaming technology where you've got like BSP portals and things like that you can use to basically tell the rendering engine, don't draw all this if the character is in this particular area and looking this way. And without that, it would want to draw all this stuff. So, of course, at this point, we're now applying an optimization technique using BSP trees in a game editor.
Right.
Okay, so it's, again, a way of dividing up our geometry. So the hidden surface removal, that's the first thing people jump on. Even with our example with Joel, we started talking about, let's not talk about the people behind you or the people in front of you. But what about things like ray tracing, where things get a little bit more complicated and making sure you're dealing with the right areas.
Right.
That's really important.
So you can start optimizing how ray tracing works.
Collision detection. Okay. Joel just shot something, right? Now, where's this projectile at in the world?
Right. We need to know all these things.
We can easily use the tree to start dumping a whole bunch of data, a whole lot of polygons. That's what I was looking to say. Because there's no way we could possibly be colliding with these. Because looking at the tree, we went on the branch that went to the left. Right. We went to the positive branch. So there's no possible way we could collide with any of the polygons that's on the negative branch, if you will. So again, just a fantastic way of optimizing what's going on in your scene, because then you don't have to look at all of the polygons that you could be possibly colliding with. You're now dealing with a smaller subset of polygons that you could be colliding with.
Exactly. And of course we have computing shadows, and there's just a whole bunch of ways.
There's a lot of things you can do with BSP trees.
BSP trees is just a data structure that allows us to, in code, find out where a particular object is.
Right. Now, I guess I just want to harp on this one last time. Again, a lot of beginners think that BSP trees is for hidden surface removal. It's not. There's a lot of different things you can use it for.
Right.
Please get that in your mind. The hidden surface removal, as a matter of fact, you're going to see with this next technique we're going to talk about, there's other ways.
Right, there are a lot of ways.
That's right. And so BSP trees, that's, as Joel said at the beginning, for hidden surface removal, that's kind of an old school approach. Okay?
It still can be used, but it's something that's more...
It can be
been
used
around for a
in
long
conjunction
time.
with other techniques as well.
Right. That's another thing that needs to be pointed out. I mean, different optimization techniques. Doesn't mean if you use BSP trees, you can't use Octrees.
That's right. Absolutely.
All these optimization techniques can work in conjunction with each other to provide better performance.
For sure.
So let's go ahead and see how to create these actual BSP trees. So we start out with the scene on the right. Let's just say we have a few simple faces.
And here's this view. Let me describe the view as you guys see it. This is a top-down view of polygons, and the little line that you see coming out of A, B, F, and H, that just indicates the normal, or what we'll just say is the front side of the polygon. And the other side without a little line sticking out, the side with the letter on it, that's the back side of the polygon.
Exactly.
Okay.
And then what we have is just simple polygons here that define some sort of level.
It's like walls.
Right, they're walls.
It's like a little maze.
So once we got that, let's design A as the root. And let's just walk through this. Again, as we said, we have the normal.
You did say an important thing, though. We're going to say A is the root.
We are going to say A is the root.
That's really important. You've always got to have a root in your BSP trees.
Some polygon to start out with.
That's right.
Someone to define the origin, if you will.
So you could use a dummy type polygon if you wanted to, something that you're not even going to show as just a reference point, as this is what we'll use as root.
Exactly. And this is one optimization technique for BSP trees as well. Sometimes after someone creates the entire BSP tree, they'll reorganize the BSP tree so that it's balanced. Because, of course, in certain trees, you could have tons and tons of nodes on the left side and very little on the right side.
For sure.
And then your tree is not very useful because you're losing the purpose of having a tree in general. So they'll rebalance that tree by changing the origin.
Exactly.
So we have our normal. And again, as we said, we have the positive side of normal and the negative side, front and back. And as we just said, A is going to be the origin. And as the resultant BSP tree, we're just going to kind of build the resultant tree on the left side here for this particular scene. So we start out with A, our origin polygon. And polygon B is on the positive side of polygon A's normal. So this guy is facing B, right?
That's right.
So this is going to be put on the right side.
Ooh, but big thing to point out right here.
Does it have to be on the right side?
Does it have to be the right side? No. This really comes down to how you have decided you're going to implement your BSP tree.
Right.
If you wanted to, it could have, the positive side could be on the left side of the node. I mean, it's up to you. In a minute, we're going to show you an application, a Java application, that allows you to basically construct BSP trees on the fly. And I think it's a really great website for those of you out there that are interested in this optimization technique. You can go and you can read through. He's got lots of code examples. He's got an applet for you to play with. A lot of neat stuff over there. And I'm going to show you guys that. But you're going to see that his BS tree is actually reversed from ours, with the positive side being on the left of each of the nodes.
Exactly.
And the negative being on the right. So again, the bottom line is this. You decide what side's positive and negative. In your code, just make sure that if you're going to have, the positive side will always be on the left. Make sure your code reflects that.
That's right.
And you stay faithful to that throughout your entire application. That's key. You can't switch back and forth or you're just going to end up with a jumbled mess of data.
Exactly. So we got our B. Now, we have polygon F, and this guy is going to be on the right side of A, so we're going to put that on the left side of the tree.
He's behind A. That's how we're looking at this.
All right.
Cool.
So now here becomes an interesting scenario. For F, we have H left, right?
Right.
Where's H relative to F?
Ooh, he's kind of in front
on the left
and
side
behind.
And behind. How does this work? Well, in this case, what we need to do is split H into two parts.
That's right.
So, see, as I said, polygon H is on the left side and right side of F. So what we're going to do is extend this F polygon so it shoots and hits H. And at that intersection point right here, we're going to split it. So we'll just call this H1 and H2. So splitting it into two separate walls. And now H1 is going to be on the front side of F, and H2 is on the back side of F. So now, simply put those guys into the tree.
And now you have a little tree, so give us an example of standing somewhere.
Okay, let's say we're standing right here. Okay. So we're
in front of A and in front of B.
Right, so we're in front of B, so we go to the right first,
right.
In front of A. We go to the right again. So in the tree, we're going to be on the right side of B.
Right.
And if we did, let's say on the right over here, on the right side of A. So we're going to choose the right side of A.
Well, let's do this. What if we were, let me steal the mouse right now.
Yeah, sure.
What if we were standing somewhere right over here?
Okay.
So where are we at? We're behind H2, we're behind F. So watch this. I can come over here, well, right here is where we're at. And I mean, it's really that simple, guys, once you get all of this implemented. Think about it. We know the right-hand side. Wait a minute, we're behind. Let me do left-hand side.
Okay.
So left-hand side, so we're behind. We're right here. Well, that means we're also behind. We have to. If you follow this back up with the way the data's been recorded, we're behind F as well. And if we're standing here, look at this. We are behind F. And this means even further, if the data's all holding up right, we're behind A as well. Look at this. So we start here. We're behind H2. We're behind F. We're behind A. Right here is behind H2, behind F, and behind A.
Exactly. So our data structure is accurately representing the position of our character, or whatever it may be.
Whatever it may be, that's right.
And that's what makes this particularly amazing, because in a simple data structure, we have positional data.
Right. Now, a very nifty website, if you guys are interested, so let's cruise over here. BSP Trees. So www.symbolcraft.com. Head on over here. He's got a PayPal, a donate link.
So donate some money.
So donate some money. He's got a lot of really information, or a lot of very useful information here. So if you go over here and you find this helpful, help the guy out. It's always a good thing. He's got an applet here that's really, really cool. It allows you to come in here and basically start drawing walls. So if I was to draw a wall right here by just simply clicking and dragging like such, check this out. Here's our little character. This is the direction we're looking. Here is our polygon. There's our normal. And here's the start of our BSP tree. Notice in this particular case, the positive direction is on the left. You know, our implementation had positive direction on the right. Again, that comes down to the programmer. There is no rule etched in stone saying that it always must be this particular way. It's just how you implement it. That's what's important here. So check it out. So again, we can only branch two ways. Right now, there is our root polygon. So if I was to come over here and draw out another polygon, okay, check it out. Our normal facing inwards. So which side did we put this on? Well, we had to put it on the positive side, in this case with his implementation. That'll be on the left. And since our character is still standing in front of 1, we have to be on the positive side of 1. Now, if I was to come up here and create a wall behind this, behind our root polygon, we would have to branch in this direction. We'd have to. So let's go ahead and draw it just so that we can see it. Look at this. We branch in that particular direction. And then it just simply comes down to, all right, well, that's good. If I draw a wall in front of polygon 2, then in front of it's going to have to go in a positive direction. So if we come over here and we draw, look at that. We go in a positive direction. So we can see that by coming in here and quickly drawing out some of these things. So we do something like that, maybe something over here. You can see how our tree starts to grow. And at any given time, we can see where we are at. If we move ourselves around over here.
And you can see we have a little 3D view.
We have a little 3D view. And what's really cool is you can come in here and you can look around. So it's a very, very nice little application that he's put together to help understand how these things work. Now, basically, wherever we're at, you can see that as we physically move, not as we look around, but as we move our character's location.
It's positional, not based on the angle.
That's right. You can see how we're updating our location, if you will, inside the BSP tree. So right now, again, the normals play a very important part here. We are behind polygon 6 and behind 4, but we are in front of, actually, let's see, we're in front of 1 and we are in front of 0. And you can follow this all the way back up. So here we are at 6, and on the right-hand side means we're behind. So we're behind 6, which is indeed behind 4, which is indeed in front of, and here's 4, in front of 1, which is indeed in front of 0. So it's really cool. I mean, it's a great, great website to go to. First of all, just use this little applet here to get a feel for how this works. You can see as my little character kind of jumps around. Look at this. I've moved myself all the way up here. And, oops, didn't mean to draw that or that. Just kidding. So I've moved myself all the way up here. Actually, that's a great thing that I did that. Let me do an easier one to see. Something like right here. You can see how, look at this. Our polygons are now being split up. So let me do this. A quick reset. Bear with me, guys. I just want to show you this real quick. So if I do something like this, and if I do something real simple like this, okay, we get that. But if I do something like this, again, our theoretical extension, which causes our polygon to be split, and now we go in two different directions. Look at this. So 2F and 2B. Check out 2B. It's behind 0, so it has to go to the right. And, of course, since this was the next polygon on our list that we're dealing with, this one is indeed in front of 1, and it is. It's in front of 1. So very useful information. This is very helpful in getting a good understanding for how the whole BSP tree thing works. And then, like I said, he's got some fantastic information, some great reading, implementation details, BSP tree frequently asked questions, etc. You can really pick up a lot of good information from this guy's website. I encourage you to head over there again. It's www.symbolcraft.com. He does have the PayPal donate link, so if you find the information here very useful to you, help the guy out. You know, come on, that's what 3D Buzz is all about. We want to help one another, educate ourselves. But really, really good stuff. So with that, let's go ahead and jump back over here into our PowerPoint show. Sorry, Joel, I didn't mean to steal and push you away like that.
No problem.
But hopefully they found that useful.
Yeah, definitely. Once you understand how it works, get your mind wrapped around it, implementing is not a big deal.
Again, he's even got code snippets over there.
Yep.
And talks about the implementation of the code in pulling something like this off.
That's right. So let's go ahead and go to the next slide here. Quadtrees and Octrees.
Ooh, now we're going to make things a lot more interesting.
Yes. So basically, BSB trees are very flexible, as we just said. I mean, it splits everything up. You get a lot of different usefulnesses, a lot of different uses for BSP trees. Octrees and Quadtrees, these are much more simplistic, but you know, they're a lot.
The BSP tree deals with a lot of data.
Yes, it does, and it does splitting and so on.
Right, which takes more time.
And with Quadtrees and Octrees, you don't have all of that overhead.
There is no splitting.
No, there is no splitting. There's simply moving data into certain quadrants.
That's right.
So basically, all you're doing in a Quadtree, for example, is you're splitting up your entire scene, be it a 3D scene or a 2D scene, into 4 quadrants, and saying what objects are in which quadrant.
And with this information, we can quickly tell what needs to be perhaps calculated in a collision, what needs to be drawn.
Right.
We get a lot of the same things offered with BSP trees. Not everything.
Not everything.
Shadows would be, well, pretty close to impossible to do. But, I mean, we still get a lot of the advantages we get from BSP trees through the use of Quadtrees and Octrees, but it's faster.
Right. Because there's just, and creating it is not difficult.
It's not as
With
complex.
BSP trees, you have to create the splitting and everything. You can't do that at runtime.
Right.
You know, that's something you do beforehand.
Right. Well, those of you out there that have ever played with, you know, the old game editors, and you got to build your level. What do you think it's doing?
Right. Exactly. It's doing the splitting. It's doing
and
all
as your
that
level
stuff.
got more complex, it took longer to build. Even before you got to the lighting phase, right?
So with Quadtrees, basically what we're doing is splitting it into 4 quadrants with Quadtrees. Octrees, it's splitting it into 8 octants.
That's right.
Which allows us to, well, split an entire 3D world up into different spaces.
Exactly.
So with a Quadtree, we basically, in a particular quadrant, we split that into another quadrant, a smaller subset as quadrants. I'm just giving an overview.
Okay.
And then
this might be hard for some people. All right, watch this. Here we go.
So
I've talked them into it. So here we go. Basically, what we've got is we've got a scene that has a sphere, a cube, a cone, and a curve in it.
Right.
Now, we have done basically a top-down projection, if you will, and we're dividing our objects up into just quadrants. I mean, that's it. It's that simple.
Like a quadrant 1, 2, 3, and 4.
And what we're going to do is we, as the programmers, are going to determine a specific direction we're going to utilize the Quadtree in. I mean, obviously, that's very important. I mean, if you pick a direction to go, we're going to start with, let's say, quadrant 1, and if we wanted to go clockwise, it'd be quadrant 4, 3, then 2.
Right.
But the thing is, make sure when you start writing your code for reading through it, etc., I mean, we really want to follow the same type patterns, because then you'll be dealing with the right data. Otherwise, you could be dealing with the wrong data quickly.
And that's bad.
And that would be horrible.
Yeah.
So we've got a nice little thing put together here. So let's go ahead and
get
do
started.
some clickies.
So, let's start doing some tree creation.
Stuff.
So we start out with here. The first thing we're going to do is put in a null. And you can just consider this the root node, if you will.
Right.
Our main scene. This is where everything starts out. So the first thing we're going to do is we're going to start out in the first quadrant here. So we start out in here. And we place our sphere in here. Notice this is the only object in this quadrant.
That's the only thing there. That's the key thing.
Right, so we're just going to throw this right into the first node here. And for Quadtrees, we're going to have 4 separate children, 1 for each of these quadrants.
Right.
So in the next quadrant, we have 2 objects. So what do we do? Well, we're going to split this guy into another set of quadrants. So this guy has another set of children as well.
So what we did is we dropped down a null, basically, and we're going to be looking for 4 nodes up underneath it as well.
Exactly. So we start out in the first quadrant of this sub-quadrant, if you will. And
again,
so we're going to put the cube.
The same implementation. If we started in quadrant 1 and went clockwise, we need to do the same here.
Exactly. So we start in quadrant 1. Quadrant 2 has nothing, so we'll just put a null in there. So we've got our null. And then we're going to go over to the third quadrant. This is a cone, so we're going to place that in here. And the last one, as you might imagine, is going to be a null.
Right.
So then we have, as you can see, 4 children for this guy as well. We go over to the next quadrant,
which is going to be our third node that's being put down, which is just a curve.
Right. So we have a curve, and then the final one is simply a null.
Right.
So you can see, very, very simply, we created this entire tree. No problems whatsoever. Very, very fast. Unlike the BSP tree, splitting, searching, etc., etc.
Now, how is this advantageous? What if we had a character that's standing down in quadrant 4, looking off to the corner of quadrant 4, so he's closer to the origin? Immediately we know, depending on the field of view, that we need to cut out. We don't need to worry about anything in quadrants 1, 2, and 3.
Right.
Period. So what I was basically, anyone that's having a hard time, if I'm standing here and I'm looking in this direction, do I need to worry about any of these? If my field of view doesn't manage to actually clip into those or cut into those, then no, I don't need to worry about it. If I shoot my weapon in this direction, my projectile is traveling in this quadrant, do I need to worry about cycling through all of my objects over here to see if there's been a collision?
Right.
No.
No. And what's really cool is this is a very simple test. I mean, we start with the first quadrant. We know that this is somewhere in the third quadrant, fourth quadrant. So we just loop through, start here, go to this one. I'm sorry. Okay, go to this one here.
That's right.
Because we're going this way around.
That's right.
So we started a null.
Joel did an awesome job, and he did this on purpose.
Yes, I did.
Of demonstrating.
We scripted that part.
That's right. Demonstrating that you must follow your implementation of the Quadtree.
Right.
Actually applies to everything. The Quadtree, the Octree, the BSP tree, doesn't matter, because if the moment you start reading it incorrectly,
everything's wrong.
Everything's wrong.
Right.
So in this case, it's in quadrant 4.
So we and the second
since that's the second one, we start here, which is a null. So now we can divide down further, and we've got all of our objects inside of it, and then we can test those.
Right.
So instead of dealing with 1, 2, 3, 4 different objects that's in the scene, we're only dealing with 2 to see if there's a collision. Much faster, 50% faster in this particular case.
And if you have thousands and thousands and thousands of objects, I mean,
you can see quickly where this could be helpful.
Very much
now, with the Quadtree, you can see this is a very simple form of optimization. It's just, again, a top 2D top projection.
Right.
That's it. What if we wanted to bring in the z-axis in this particular case?
Right, we want to divide our scene more.
That's right. This is where we're going to get into, dun dun dun.
Let's just finish up.
There we go. Octrees. I like that for a cool picture.
Ooh,
I
nice.
like it, Joel. You did good.
Thank you.
So basically what this is it's a quad tree. And a quad tree, and a quad tree, and a quad tree, and a quad tree, and a quad... No, we just got 2 quad trees, one stacked on top of the other.
One here and one over there.
That's right, that's right.
Or you could view it as one on the top and one on the bottom.
That's how I like to view it. One on top and one on bottom, because we're now dealing with depth.
Right. So basically we have 8 extra areas to work with. So now we can divide, let's say, this is part of our level, this is another part of our level, et cetera, and we can just divide it up really, really nicely.
And again, it comes down to how you decide to implement the techniques of walking through this. I mean, we could start out right here, and we could walk around like such, and then step down, and then walk around down below like such. An interesting thing to keep in mind is now we do start dealing with a bit more data, because if we end up with a couple of different objects inside one of these quadrants, what are we going to do? An octree inside there as well. We're breaking it up even further because we're dealing with depth.
So now each of our trees, each of the nodes in our trees has 8 children.
That's right.
Right, so that's the only change. So quadtrees, and octrees are very,
very
similar.
It's just octrees are dealing with more data because we've now put depth into the whole picture.
If you're working with, say, just as an example, a 2D strategy game, and all you're really working with is on one plane pretty much, you want to use quadtrees. If you're dealing with a lot of depth changes, like some 3D first-person shooters...
Got characters up on catwalks up above me, and I'm trying to figure out collisions. Do I need to be... And I've shot up. Do I need to worry about my bullet hitting anything in front of me?
Right.
No. I can now immediately in code take a look above me in that area, and now I'm worried about colliding only those objects.
Exactly.
Ooh, I'm talking way too fast. So really, that is a couple of very handy optimization techniques when dealing with 3D worlds, if you will. I employ you guys to go out and search around on the internet. Look at there's tons and tons of sample code out there.
Again, we could cover 5, 6, 7 hours just on this.
Just on BSP trees, to be honest with you. Yeah, this. Employ you guys. I just realized what I said. Wow. But anyways, there's a lot here. This is a very heavy subject. And like I said at the beginning, the idea was to present a discussion that got you guys thinking about optimization techniques, showed you a few of the techniques that are available out there, and put you on the right track for getting these into your own applications.
That's right.
So hopefully this has served to be a great help. And in the future, I'm sure we'll end up doing some other C++ VTM that's going to be utilizing some sort of optimization techniques.
That's right.
But in this case, where we're just exploring OpenGL itself, I just want to make sure that you guys don't forget about how important it is to optimize your applications. Yes, you may be showing polygons and all, and you've got some really cool world, but how impressive is it if you're getting 1 frame per second?
Exactly.
So keep that in mind. So with that, that's going to wrap up this lesson, and thanks a lot for listening to us, guys.